Hello, everyone. It's a great honor to speak, honor to present our work, characterizing and emulating FDP SSD with WARP, abbreviation of Right Amplification Research Platform. I am Inho from Virginia Tech. Shoaib, Asif, Javier, Matias, Sam No, and Huaicheng Li are the co-authors of this paper. Thanks to Samsung and Western Digital for supporting this project, and now let's begin. Nowadays, SSD are the main storage unit in storage systems, widely used to serve various kinds of services. The right amplification problem yet remains a fundamental challenge for SSDs. Flexible data placement, briefly called FDP SSD, is an emerging SSD that promises to reduce right amplification with simplified and transparent interface. Here's a brief comparison between conventional SSD and FDP SSD. Figure on the left shows the data layout of conventional SSD. Assume that SSD have to serve different types of data. When serving different types of data, eventually SSD places the data from different data being physically interleaved across blocks. However, in FDP-enabled SSD, data is explicitly grouped and isolated. How? By reclaiming unit handles, named RUHs. By steering writes across the RUHs, FDP can lower right amplification. One moment, please. There's a little issue. Okay. So these are the main terms for the FDP. First, RUH, reclaiming unit handle. This is specified in the NVMe request field and tells the device where to place the data. If you're familiar with multi-stream SSD, think of it as equivalent to a stream ID coming from DNS background. This works same as a zone ID. Second, reclaiming unit. This is typically mapped to NAND superblock and represents the unit of space the device manages internally. For those of you coming from a DNS background, again, the quick mapping for RU is shown. Despite FDP's promise of data placement control through RUH handles, the lack of transparency makes it difficult for user to evaluate WAF on their production workloads. And for the vendors who design optimal FDP-capable controllers. To open this black box, we organize our work around three research questions. First, when does FDP deliver near 1.0 WAF, and when does it fail? In other words, what are the root causes that prevents FDP from eliminating right amplification entirely? Second, even under the same workload, FDP outcome can be very various across vendors. Which vendor level configuration drive these differences? And third, what are the design trade-offs in SSD? What are the fundamental design trade-offs in FDP SSD? What is still hidden? Intrinsic behavior still left and uncovered, and yet answered. To answer these questions, we make 4 contributions for our paper. First, we conduct a systematic study of commercial FDP SSD, spanning synthetic, trace-driven, and file system workloads, revealing when FDP SSD sustains near 1.0 WAF and when it collapses. Second, throughout this study, we identified 2 previously unreported behaviors, RUH interference and premature recrimination, that explains how and why FDP benefit erodes. Third, go beyond what black box hardware can reveal. We design and validate WARP, the first FDP emulator that reproduces real hardware trends while exposing GC victim selection and tunable device geometry. And furthermore, with WARP, we further explore firmware strategies that are hidden in current hardware. These are the contributions of our talk. I'll cover this I'll cover the topic in detail as shown here, starting with the characterization study of FDP. Okay, let me give you a brief overview of how it's set up. So our characterization study spans 3 layers: application, system, and device. At the application layer, we cover 3 types of workload: cache-lib, file bench, and also we'll use F2FS, and synthetic workload. For cache-lib, we replace the real production traces, giving us a realistic trace-driven behavior. And second, the file bench, which run file system benchmark, allowing us to evaluate FTP under file system operations. Synthetic workload using FIO with 3 configuration, giving us a more controlled, tunable experiment to isolate specific FTP behavior. At the system level, we are testing F2FS, which is in our paper. And we tested 2 different devices, FDP SSD-A and FDP SSD-B. But due to the visibility, we implement and evaluate the warp, our observable emulator, which gives a better visibility for the other FDP SSD and better understanding with the visibility that warp provides. So takeaways that we conduct first systemic study for FDP SSD and across synthetic, trace-driven, and file system workload. I cannot cover all these workloads, so I'll briefly cover the synthetic workload for today. Okay, the main focus for synthetic workload is the 3 writes thread. This is the workload combines a random write thread, sequential append thread, and there's an additional one, an override thread that overrides with different distribution. It's pretty much like a simulated log structure file system workload, but with FIO. For the override thread, we vary invalidation distribution to sweep across different skewedness level, from high to low, with a different GPM pattern, and it can be 80-20 distribution. And before we dive into the result, let me quickly explain how to read the figures throughout this section. So this is an example of write amplification. Y-axis shows the write amplification factor, or WAF, so lower is better. X-axis is a workload size, which is a relative number to the device capacity. So it is represent X0, 1, 2, which means the workload size is equivalent to 2 times of device capacity, etc. So going back to the question, so let's decide whether FTP delivers its promised benefit. Under high skew, CPM alpha 2.2, FTP maintains near 1.0 WAF throughout the experiment. As we move to medium skew, WAF stays relatively low, but under the low skew, the 80-20 distribution, WAF climbs significantly as written data volume increases. In short, when the workload is FTP friendly, with concentrated skewed data, FTP works well. But when the skew is low, FTP begins to struggle. So in short, FTP benefit depends on the workload skewness. So second factor is a firmware design. We're looking at the different vendor result under the same workload, a low skewed workload. Turns out 2 different vendors show significantly different trend under the exact same workload. So same workload, same FTP interface, but the firmware behind the scene makes all the differences. Second takeaway is that FTP benefit depends on the firmware design. Third factor is the host side data classification. I want your attention to the green line mixed FTP, which represent the case where the sequential and the override thread shares a single RUH, so it's a case of co-location, rather than being fully separated. On the left, under high skew, the green mixed FTP line overlaps with the blue FTP line over there, meaning even imperfect classification can still achieve FTP-like benefit. But under the medium skew, mixed FTP suddenly degrades to match no FTP. The takeaway here is FDP is quite fragile and easy to fail. Often FDP heavily depends on first workload skewness, second firmware design, and quality of the host classification. So when we're working with the commercial SSD, we are essentially dealing with a black box. And there's a lack of visibility into what's happening internally. The behavior is also vendor dependent, meaning results can be various across different manufacturers. And ultimately, it's hard to reason about the performance characteristic and internal mechanism. WARP, our open SSD emulator in this context, helps the situation. We offer great visibility into inner working of the device, and it's completely vendor agnostic. And so our research findings are not tied to any specific hardware. Eventually it gives a great reasoning. We can observe, analyze, and understand exactly what's happening in every layer. To go beyond what black box hardware can reveal, we built WARP, FEMA-based FDP SSD emulator. As you can see in the architecture diagram, GuestOS communicates with WARP through the NVMe interface, just like it would like a real device. Inside WARP, we have a FTP FTL layer. At the basic level, FTP layer includes RU and RUH management, along with RUH-based data placement. So writes are direct to the correct reclaiming unit based on the host hints. For advanced FTP logic, we implement a firmware framework for RUH-aware garbage collection. So now finer grain garbage collection is possible rather than globally picking a victim. Optimizations such as lazy garbage collection and block remapping, which is allowed to defer expensive GC operation and study their impact more precisely. And which is more critical is that WARP exposes what real hardware hides. So on the NAND geometry side, we support configurable NAND geometry. You can tune the parameters like a reclaiming unit size and over-provisioning ratio to match different device configurations. On the observability side, we provide per-RUH level monitoring, which is really helpful for this project, and per-GC level counters, giving us a fine-grained visibility and it can now truly understand how FTP behaves under different workloads. I won't go into more detail about this design capabilities today, but feel free to check our paper in the full picture. So with WARP in place, let's now validate it against real hardware, and let's look at what it can reveal. So one essential property an FTP emulator must have is WAF reproducibility. It should match trend we observe on the real SSD. So here we are looking at one of our results to capture the right identification trend for both real SSD and WARP. The key point is that WARP reproduces a similar right identification trend compared to the real hardware. For more comprehensive validation across different workloads, please check out the paper, whether we are doing correctly or not. With WARP observability, we can now look inside the black box. So first finding is what we call the noisy RUH. This is a right identification breakdown graph, and in the WAF breakdown workload, by the workload, under the low skill, RUH0 handles approximately 90% of the written data volume, the IO size, goes to RUH0, while RUH1 and RUH2 account for 5% each of the workload. Yet these small volume RUHs contribute disproportionately to WARP. Even roughly 5% of the data can be responsible for 20% of total right identification. So not just the amount of this culprit, a single noisy RUH can eventually inflate the global right identification significantly. So yeah, that's the first finding. And the second finding is what we call safe sequential, looking at the same WAF breakdown. And we noticed that RUH0, the sequential data, still contributes significant amount of right identification across all skewed levels. This happened because the sequential data, despite containing mostly valid data get reclaimed prematurely by the garbage collection. We coined the term safe sequential. Sequential data can be reclaimed prematurely in FDP devices. The insight is that GC should protect capacity-dominant sequential RUHs from being over-victimized. Due to the time constraint, there are more papers that I would love to, but I'll briefly mention here. There's more characterization study, cache slip, F2FS, and also there's a really fruitful insight that you can observe in our paper, the placement policy trade-off. And additionally, there's a little salt of grain and the warp-guided optimization in cache slip, which is a case of optimization in cache slip. Please refer to the paper more details. So to wrap up, we tried to cover 3 questions for question 1, question 2, question 3, and this is listed as it here. Thank you for paying much attention, and yeah, I'll get the question.